If we reverse the idea of a heat engine, which takes energy from a heat source and dumps it to a cold sink and produces work to the surroundings, we turn that backwards, we should be able to provide work from the surroundings, from an electric motor, let's say, and take energy from a low temperature source, Q low, and pump it to a high temperature sink, QH, just the opposite of a heat engine. That means we'd have to reverse the cycle. If the cycle runs in reverse, we'd be starting here, and the first thing that we'd be doing from step 1 to step 2 is we'd be doing an adiabatic expansion. That means no Q, but it means there's a work output. So work comes out of the system, work 1, 2 we'll call it. The next step from 2 to 3 is isothermal expansion. Well, that means work comes out, work 2, 3, but energy goes in, Q low, the same amount of energy as there is work. So Q and W match each other. Then there's an adiabatic compression from 3 to 4. So that means work goes in, we'll call it work 3, 4, but there's no Q because it's adiabatic. And then there's an isothermal compression back to step 1. In isothermal compression, work goes in, we'll call it work 4, 1, and Q comes out. And we'll call that Q hot. So Q low goes in during this expansion, Q hot comes out during the compression. So this is a way of pumping heat. And just like we saw before, work 1, 2 and work 3, 4 are going to be the same. So QH and work 4, 1, Q low and work 2, 3 are going to be equivalent to each other. Heat pumps really exist. They're not just fictitious. 3 common places where these show up, one not as common as the other 2. Refrigerators and air conditioners do this all the time. Almost everybody in our country has a refrigerator in their house that takes energy from a cold temperature inside and pumps it to the outside where it's warmer. And there's a motor in there that does that. There's work that's done. Air conditioners do the same thing, only you're not refrigerating just a small compartment. You're refrigerating your whole house or a room that the air conditioner is in. Geothermal heating systems are not as common, but maybe will be as the price of fossil fuels continues to rise. Geothermal heating systems take energy from the ground where it's cold and pumps it into your house where it's warm. So it's like a big giant air conditioner that uses the earth as a heat source. We don't use efficiency in the same way we use it for heat engines. For heat pumps, we use something called coefficient of performance, or COP. Here's what the coefficient of performance is. COP is the heat moved over the work it takes to move it. If you're talking about a refrigerator, what you're interested in is how much energy can you move out of the cold place. And so for a refrigerator, COP is defined this way. COP is Q low over work. For a heat pump, like a geothermal heat pump, COP is defined a different way. COP for a heat pump is Q hot over work, because you're interested in knowing how much energy can you move into the hot place, which is your house or whatever you're heating. So here's an example problem. Heat pump has a coefficient of performance of 3, and it's rated to do work at 1500 watts. Remember, 1500 watts means 1500 joules per second. Here's the question. How much heat can it add to a room? So that'd be QH is what that would be, per second. Looking at our definition of coefficient of performance, COP is Q hot over work. So that means Q hot, which is what we're trying to find, would be equal to work times the coefficient of performance. So for our situation here, the work done was 1500 watts or 1500 joules per second times a coefficient of performance of 3. So that gives us 4500 joules per second. So in a second's time, 4500 joules could be moved into the room. Here's the next question. If the heat pump is turned around and run as an air conditioner in the summer, and this works with heat pumps, you can actually do this, what is the coefficient of performance for this use as an air conditioner? Here's what we know. The coefficient of performance, if it's an air conditioner, is Q low over work, not Q hot over work. So we've got to figure out what is Q low. Thinking about the schematic diagram, here's the heat pump itself, the engine, and we know that the work that this thing can do is 1500 watts, 1500 joules per second. We know also that it can deliver 4500 joules every second to the hot sink. So the question is, what's Q low? How much energy can it take out of the room? Well, by conservation of energy, Q low is going to have to be Q hot minus the work, the 4500 joules minus the 1500 joules. So if you take 4500 joules and subtract 1500 joules, you end up with 3000 joules. So this heat pump has a Q low, it can extract 3,000 joules every second from the room. So what's its coefficient of performance? Well, COP is Q low, which we now know is 3,000 joules, over the work input, which is 1,500 joules. So its coefficient of performance as an air conditioner is 2.0. Here's another question. So, what is the highest possible coefficient of performance for a heat pump that's moving energy from a 0 degree outside to a 21.2 degree Celsius room? Let's define coefficient of performance first of all. Coefficient of performance for a heat pump is QH divided by work. So those are the terms that we're going to have to find somehow. Looking at our schematic diagram, let's try and make sense of this because we don't know either work or Q hot. We have to find a relationship here. Q low enters the heat pump from the low temperature source. Work enters from the source of work, electric motor or something, and Q hot exits the heat pump into the high temperature sink. By conservation of energy, here's what has to be true. The work done has got to be equal to the difference between how much energy comes out and how much energy came in from the heat source. So we could rewrite this. We could say coefficient of performance is equal to Q hot over Q hot minus Q low. But we've seen that these ratios of temperatures and ratios of heat are equivalent to each other. So we could say COP is equal to T hot over T hot minus T low. Now we're going to have to use Kelvin temperatures to make this work out. So let's convert. First of all, we have 21.0 degrees C, 21.2 degrees C. If we add 273 to that, we come up with 294.2 kelvins. And the other one was 0 degrees C, and that's 273 kelvins. So we can plug these numbers up here. 294.2 kelvins over 294.2 kelvins minus 273 kelvins. And this ratio is going to be unitless, and it's 13.9. Now the next question is, what's the smallest power rating the pump must have? In other words, how little energy can it provide per unit time to move 3,500 joules into the room in a 24-hour day? Okay, going back to our problem, here's part B. We know the coefficient of performance is Q hot over work done. That means that the work needed is going to be Q hot over the coefficient of performance. Well, it's supposed to move 3,500 joules with a coefficient of performance of 13.9, so 152 joules. That's in a 24-hour period. So we want power. Power is work over time, so it's 252 joules over 24 hours. But we want watts, so we'll convert to seconds here. 1 hour is 3,600 seconds. And when you do this calculation, you come up with 0.07 joules per second, or 0.07 watts. That's a really small power input. And so you see where there's a great appeal to have geothermal heating systems, because that's what these heat pumps basically are, is geothermal heating systems. That's not very much energy at all. It's extremely small amount of energy. And if the heat source, the low temperature heat source, is free, well, you can see where this could be a very efficient heating system. The problem is it's very expensive to dig down into the ground and lay all the pipes that are required for these heating systems. But as the price of fossil fuels goes up, that might look more and more attractive for more and more people. And I think we'll see an increase in the use of geothermal heating systems like this. Our last topic is about the second law of thermodynamics. And we'll start out by asking this question: why doesn't it work to cool down your kitchen by leaving the refrigerator door open? If you just lifted the refrigerator door open, why wouldn't that cool down the whole kitchen? This is related to the second law of thermodynamics. Here's one thing that we know. Energy flows through heating from a hot object to a cold object. So this is an object with a high temperature, this is an object with a low temperature. We're going to get energy flow through Q from the hot to the low temperature. For the whole system, the energy is the energy of the hot object plus the energy of the cold object. Now let's look what happens during this change. There's Q. The Q for the hot object, change in temperature of the hot object, well, that's equal to Q, but it's a negative number because it's a loss in energy. The change in temperature of the cold object is equal to positive Q because it gains energy. But the energy that flows between them, if this is all well insulated and there aren't any losses, it's the same number. So the change in energy for the whole system is minus Q plus Q, which is 0. So that doesn't violate the first law of thermodynamics. The total amount of energy change is zero for the whole system. Now let's look at something that never happens. We never see this happen. You never say a low temperature and a high temperature object, and low temperature object has energy flow into the high temperature object so that the low temperature object becomes colder and the high temperature object becomes even hotter. Why would that happen? Let's see if the first law of thermodynamics explains it. Again, total change in energy would have to be equal to the change in the energy of the hot object plus the change in the energy of the cold object. Well, the energy of the cold object has changed by negative Q. Delta E for cold is negative Q because it's lost energy. Delta E for hot is positive Q because it's gained energy. But it's the same amount of energy. So this would be equal to minus Q plus Q again, which would be zero. So there's nothing in the first law of thermodynamics that prohibits this from happening. The total energy change for the system would still be zero. That means there must be another explanation. And that explanation is the second law of thermodynamics. This is stated in a lot of different ways for different purposes, but this is the one that's related to heat engines. This is called the Clausius version of the second law of thermodynamics, and it's this. Heat naturally flows from a hot object to a cold object. Heat will not spontaneously flow from a cold object to a hot object. That will not happen. So that's the Clausius version of the second law of thermodynamics. It's stated in other ways, and if you take more science classes, you'll hear it stated in other ways too. But this is the simplest way of understanding the second law of thermodynamics. Hot things get colder, cold things get hotter. It doesn't work the other way around.